Have you ever been handed a super complex engineering design and just felt completely lost in a sea of lines and symbols? Well, today we're going to crack the code. We're talking about how to turn those dense, technical blueprints into clear, compelling stories that pretty much anyone can understand.
Right, so this is what we're up against. This is a typical engineering drawing. It's dense, it's technical, and let's be honest, it's kind of a headache to look at. All the critical data is right there, but the story, the why, it's missing. So the big question is, how do we unlock the brilliant ideas trapped inside this blueprint and really make them shine?
All right, we're diving into explaining extreme engineering. Our challenge, making the invisible visible. And to do that, we're going to look at a piece of engineering that's pretty much hidden in plain sight. We're using the humble pressure vessel as our guide to see how we can bring these incredible designs to life.
You know, these things are the true hidden workhorses of our world. They're in the power plants that light our cities, the refineries that fuel our cars. They are everywhere. These massive containers are silently operating under absolutely immense pressure just to keep our modern world running. But behind that simple-looking exterior, there is a whole world of mind-bendingly complex engineering. Okay, Section 2, One Vessel, Five Worlds. The subtitle says it all, how design changes based on what's inside. And this is the key takeaway, really. Not all pressure vessels are created equal, not even close. Trying to use the same vessel in two different industries, it's like comparing a bicycle to a rocket ship. The physics are just fundamentally different. A vessel built for a simple water treatment plant would be vaporized instantly in a refinery. The design is a direct reflection of the world it has to survive it. And this table right here, it tells the whole story. Just look at the extremes. A power plant vessel has to handle over 100 bar of pressure at a scorching 500 degrees Celsius. Now compare that to a water treatment tank sitting at less than 10 bar. We're not just talking about a small difference here. This is a completely different engineering reality. It requires a whole new set of rules, a whole new set of materials. So, how do they figure it all out? Well, this formula, right from the ASME code, is basically the engineer's secret weapon. It's the unbreakable rule that determines exactly how thick a vessel's walls need to be. And see that little P for pressure? That is the star of the show. The more pressure you have, the thicker those walls have got to be. It's simple physics, really, but it's also the razor-thin line between a safe design and a catastrophic failure. Okay, next up, deconstructing the design. We're looking at the universal parts of every pressure vessel. Because despite all their different jobs, they all share a kind of common anatomy. So let's pop the hood and break one of these engineering marvels down into its essential building blocks. So every vessel is going to start with the main body, right? The cylindrical shell. Then it's capped by top and bottom heads. You've got nozzles so things can go in and out, a support skirt or saddles to hold the whole thing up, and manways for access. You can think of this as our universal toolkit for building pretty much any kind of pressure vessel you can imagine. And this quote from the source material just illustrates the point perfectly. For an oil and gas separator, the focus isn't just on handling extreme pressure. It's about efficient gas-liquid separation. That means the internal design, things like baffles and trays, is what's really key. It's not about brute strength alone. The form is tailored specifically to the job it needs to do. All right, we've seen the complexity, we've seen the components. Now, how in the world do we bring it all together in a way that's actually easy to understand? The answer lies in a super powerful visualization technique that transforms those flat, boring blueprints into dynamic 3D stories, a lot like what you'd see in a professional BIM, or Building Information Modeling presentation. It's a beautifully simple yet really powerful three-step process. First, you start with that traditional engineering drawing. Then, you bring it to life as a realistic 3D model, and we're talking a true Revit-style metallic look. You set it against a steel gray background, give the vessel a chrome finish, and maybe make key pipes in electric blue so they really pop. You add realistic lighting, reflections, and shadows, and suddenly the design feels tangible, like you can reach out and touch it. And finally, you make it move. You use dynamic camera angles to zoom in on critical welds, you orbit the entire structure, you can even explode the view to see how every single piece fits together perfectly. And here's the real magic, okay? This isn't just about making a cool-looking model for a presentation. It's about building a bridge from mind-numbing complexity to crystal clarity. When a project manager can virtually walk around the design, or a safety inspector can see a potential weak point before a single piece of steel is ever cut, the entire project just becomes safer and way more efficient.
Let's move on to the full 3D story. It's time to apply this method and see the difference. We're going to put this technique into action with the concepts we've just discussed, and you'll see just how dramatic the difference really is.
And this is where it all just clicks into place. On the left, you have a refinery hydrocracker facing down over 150 bar of pressure. On the right, a water treatment tank at just 8 bar. The wall of that refinery vessel is more than 10 times thicker. The testing requirements, they are worlds apart. Visualizing this contrast makes the engineering challenge instantly, and I mean instantly, understandable.
Just let that number sink in for a second. 150 bar. That is over 2,000 pounds per square inch. It is an absolutely immense amount of force, contained day in and day out by brilliant engineering and cutting-edge material science. When we say extreme, this is what we mean. And this is where 3D visualization becomes an absolute game changer. With these models, we can literally pinpoint potential problems before they ever happen. We can see where corrosion might take hold, we can see where a weld might crack under stress, or where high-velocity fluids could start to wear away a nozzle. We can even visualize creep, that slow, silent deformation of materials under constant high heat. It's like having a crystal ball for engineering. It's incredible. So, what's the bottom line here? It's pretty simple. When we can clearly see and share the story behind a complex design, we empower the entire team. It just leads to smarter decisions, more effective collaboration, and ultimately a safer and more successful project for absolutely everyone involved. So, we've seen how a simple, flat blueprint can be transformed into a powerful 3D story, unlocking the secrets of incredibly complex engineering. The real question, though, is what hidden stories are waiting to be told in your own designs, and how are you going to use these tools to bring them to light?